All right, next up in our conversation about circles, we've got a couple of things we want to talk about here. The first of which are chords. We want to get into chords some more. A lot of properties of chords, a lot of things that we can do with chords that are drawn in circles. And so that's what we're going to get into now. So, some theorems for you. Okay? At any time, if you need to keep, stop the video and draw things out, go ahead. I'm going to go ahead and talk through. But first theorem here, in the same circle or in congruent circles, has to be that way. But two minor arcs are congruent if and only if their corresponding chords are congruent. So what we need to understand is every time we talk about a minor arc, so arc AB, there are endpoints, A and B. Well, those endpoints can be endpoints of segments as well, which are chords. So what that means is every minor arc has a chord that sort of corresponds to it, and vice versa. Every chord has a minor arc that corresponds to it. Well, if in the same circle or in two congruent circles, if these chords are the same, so if AB and AC are congruent, then the arcs AB and AC are congruent, and vice versa. If the arcs are congruent, AB and AC, then the chords AB and AC must be congruent. Okay? And so we have an example here of how we can use that. So in the same circle, we've got these two chords, AC and CB, that are congruent. Now, we want to find BC. Don't know what BC is? Let it be X, that arc. But since these chords are the same, these arcs are the same, so AC is going to be X as well. And then we know, of course, that all the arcs of a circle must add to 360, so we're simply going to add these guys up and set it equal to 360. Okay? And so arc BC must be 122 degrees. All right? Next theorem says that if one chord is a perpendicular bisector of another chord, so JD is a chord in this picture, AB is another chord, and if JD is a perpendicular bisector of AB, then the first chord is a diameter. In other words, JD has to be a diameter. It has to go through the center. Okay, so some things that we have to know. Two chords here, and what we would have to know is that, first of all, JD and AB are perpendicular, which means they make right angles, right? Then we would have to know that AC and CB were congruent, which means that JD is bisecting AB. And if that happens, that means JD has to be a diameter. It has to go through the center. Okay? How do we use that? Well, we've got an example here, right? Some things that we have to know. And right now what we know is that this chord, and we need another point here, so FD is a diameter. And it's perpendicular to the chord EG. So if we know that, then that tells us that these two segments, that chord EG has to be bisected, which means that we can take 3x plus 16 and set it equal to 12x plus 7 and go solve this. And when we do, x ends up being 1. Okay? Next theorem, okay, actually builds on the previous one. So we're back to looking at this chord JD as a diameter, and we know it's a diameter because, again, it's perpendicular to chord AB and it's bisecting it. If that's true, we know it's going to bisect the chord AB, but what also happens is it bisects these arcs that are behind the chord. So arc AD and arc DB are going to be congruent as well. Okay? So we can use that. So we're in this example here. If we want to find the measure of arc PQR, and we're calling it arc PQR because we don't know if it's a minor or a major arc just yet, it's probably going to have to be a minor arc. So PQR or arc PR? Well, we know that here that SQ is a diameter. It's perpendicular to PR, and it's bisecting PR, which means it's also bisecting. It's also bisecting these chords, or sorry, it's also bisecting this arc here. Okay. So if arc PQ is 40, then arc QR is 40, which means that the whole arc PQR has to be 80. Okay? Make sense? All right. Another theorem, and there's a bunch. Okay? But we're still talking about chords. Two chords are going to be congruent in the same circle or in congruent circles. Again, the circles have to be, we have to be in a circle or two circles that are the same size. Otherwise, all bets are off. And it's because these circles are, circles are curved. But anyway, two chords are going to be congruent if they are the same distance from the center. So what does that mean? We got to think about it, some things, right? We've got to look at, first of all, how do we measure the distance from a point to a line? And the distance from a point to a line has to be right at it, right? We're not going to measure the distance from point F to chord AB out here or out here. It doesn't make any sense. We're going to measure it straight at that chord, so at a perpendicular. All right? Well, same thing here. From point F to chord CD, we have to measure it at a perpendicular. So we have to consider segments from the center to the chord that are perpendicular to those chords. And if those segments are the same length, if they're congruent, so if EF and FG are congruent, then the chords themselves have to be congruent. And that makes enough sense, right? AB and CD are going to have to be congruent. It makes sense because if chord AB were further away from the center, so if we push that out, you have to sort of imagine this, right? Then you would have a chord that's the same length, but not on the circle. So we have a segment that's the same length, but the endpoints are not going to be on the circle. So it's not a chord anymore. We have to shrink it down, which means that it's not the same length. Okay, so if they're the same distance from the center, then the chords have to be congruent. They have to be the same length. All right? Sorry about that. Example, how are we going to use this? Okay, so some things that, again, we're going to have to know. We're going to have to know that the center here, from the center to the chord, each chord, the distance is the same. And here's how we're going to know that. We're going to know that these segments are perpendicular and that these segments are congruent to each other. And then we'll know that the chords are the same length. So that means we can come in here and go 3x minus 11 and set that equal to x plus 9. We get 2x equals 20, x equals 10. Okay? Got to know those theorems and how to use them. Okay, next section talks about inscribed angles. So now we're going to move away from chords and talk about some more angle stuff. Okay, inscribed angles and polygons. Well, what does that mean? Well, it means vocabulary. We've got to know what some of this stuff means. An inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. So here's our circle. An inscribed angle is different than a central angle. Remember that a central angle has its vertex at the center and touches the circle, right? Extend the sides out to touch the circle. So that's a central angle. Inscribed angles have their vertex on the circle. And their sides are chords, right? Its sides are chords. So BA and BC are chords because their endpoints are on the circle. So that's your difference. So angle ABC is an inscribed angle. Okay? Now you see the definition of an intercepted arc. It's the arc that lies inside of an inscribed angle. And you can kind of think about it as an arc that sits inside of a central angle also. But at any rate, arc AC, that's what got cut off here. But arc AC is an intercepted arc. Okay? Another definition for you. An inscribed polygon in a circle. Okay? So inscribed angles, vertex on the circle. It is possible to take a polygon that has a bunch of angles in it, right, and inscribe it in a circle, which means that all the vertices are going to be on the circle. Okay? That's what an inscribed polygon means. Now, if the polygon is considered to be inscribed, means written or drawn inside the circle, wholly inside the circle, then we can consider the circle as circumscribing the polygon. Remember, circum means around, scribing means draw, so we can draw a circle around the polygon. It means making sure that all the vertices are on the circle. Okay? We'll come back to that in just a minute. Now, the measure of an inscribed angle. I need to spell measure right. Okay, I'm going to draw a central angle in here again, and you don't need to. But I want to show you this. So, inscribed angles versus central angles. They can intercept the same arc. But look at these angles. Does this guy and this guy, do they look like they're the same size? Now, I hope you're thinking to yourself, no, they don't look like they're the same size, because they're not. Central angles are going to be bigger than inscribed angles. Central angles are equal to the arcs. The arc measure and the central angles are the same. They have the same measure. Inscribed angles are actually half the measure of its intercepted arc. So it is smaller than a central angle, and it's exactly half of a central angle, right? And I don't like this. Okay, we're going to write it a little bit differently. But if angle B is 30 degrees, then the arc, so the angle is going to be half the arc is going to be twice the angle, so the arc has to be 60 degrees. Now, I like to think of this more as the central angle is equal to the arc divided by 2. And we can get to 60 using a formula also. The angle is 30, so to find the arc, just multiply both sides by 2. And so the arc ends up being 60. Okay? All right. Then we can talk about if we're going, if we have multiple inscribed angles. And it makes sense to talk about this. Anyway, multiple inscribed angles that intercept the same arc. We can't talk about that again with central angles up here, because there's only one central angle that's going to intercept that arc AC. Inscribed angles, there can be a bunch. Okay? So, for example, angle B intercepts, if we trace it out, angle B intercepts arc AC. Well, if you trace out angle D, it intercepts arc AC also. As a matter of fact, if you wanted to, you could keep making inscribed angles that intercept the exact same arc from anywhere. There's an infinite number. Okay? Well, if they're all intercepting the exact same arc, that's going to have one measure, then they're all going to be half the same measure, which means that all of these guys are going to have to be congruent. And that's what this theorem says. It says if two inscribed angles of a circle intercept the same arc, then they're going to be congruent. So angle BAD, or angle A, is going to be congruent to angle BCD, or angle C here, because they intercept. If you trace out the angles, they intercept the exact same arc BD. Okay? So, a couple quick examples here to try to bring this together. So we want to find the measure of arc BC. Well, simple enough. We know that since arc BC is here, the endpoints of arc BC are here, we can trace this back to a vertex. And the vertex is on the circle. So that means that the angle is going to be the arc divided by 2. The angle is 38 degrees. We want to find the arc. So simply multiply both sides by 2. Okay? So the arc is 76 degrees. 76 degrees. And the same thought process works for arc BC here. We're just going to multiply 78 times 2 and get 156, and that's going to be the measure of this arc. Okay? All right. Some more theorems. Of course, more theorems. Lots of theorems for circles. Now, we're going to talk about inscribing a couple of different polygons. The first one is a triangle. If we inscribe a triangle, if it's a right triangle, then the hypotenuse is going to have to be the diameter. Okay? Makes enough sense. This is this guy right here, this angle B is the right angle for this right triangle. And if we trace it out, it intercepts this arc right here. Since this angle is 90, the arc's got to be 180. And anytime you have an arc that's 180 degrees, it's a semicircle, which means that there's a diameter that shares the endpoints. So the hypotenuse has to be the diameter. Has to be that way if you're going to inscribe a circle. Or sorry, if you're going to inscribe a right triangle. Okay? The other one talks about if you're going to inscribe a quadrilateral. In order to inscribe a quadrilateral, the opposite angles have to be supplementary. So angle A and angle D have to add to 180. Angle B and angle C have to add to 180. And that makes enough sense too if you think about it. Angle C is here, and it intercepts this arc. Angle B is the opposite angle, and it intercepts this arc. So together, they intercept the entire circle, which is 360. Inscribed angles are half of their arc. So if together they intercept the whole circle, which is 360, that means that together they have to add up to half of that, which is 180. And so that's our quick little proof on why these opposite angles have to add up to 180 or be supplementary. And then we could do the same thing for angle A and angle D. Okay? So, again, some quick examples for you to be able to, of how we can use these theorems. So, number one here, we want to find the measure of angle C. Well, because CB is a diameter, that means angle A has to be a right angle, which means this is a right triangle. So, to find this guy, we can do 90 plus 50, which is 140, and subtract it from 180. And so this angle is going to be 40 degrees. Same thing for number 2. Because AB is a diameter, this is going to be a right angle, which means this is a right triangle. So a shortcut here means I can just take 64 and subtract it from 90 because the acute angles in a right triangle are complementary. And you get 26 degrees. Okay? A couple more examples, and we're going to talk about using the fact that a quadrilateral can be inscribed in a circle only if what? The opposite angles are supplementary, right? So can this quadrilateral be inscribed in a circle? In other words, are the opposite angles supplementary? Well, we can tell right away that 130 plus 70 is 200, and so not supplementary. So you're not going to be able to inscribe this guy in a circle. Okay? Now, are we going to be able to inscribe this kite? And this is a kite. Okay, well, you add these two opposite angles up, and they do add to 180. That's no problem. But we don't know the other two angles. But we can find them. Because in a kite, these angles that are in between the non-congruent sides are the same. They're congruent. So let them both be x. And we know that in a quadrilateral, all four angles have to add to 360. So we could do x plus 130 plus 50 equals 360, which means that this is 2x. This is going to be 180. So subtract 180 from both sides, and you get 180. which means that each of these angles are going to be 90 degrees. Okay? So since they're both 90, they add to 182. So both sets of opposite angles are going to be supplementary. So you're going to be able to inscribe this kite in a circle. Okay? All right. Some examples for you. So work these out real quick. Stop the video. You can start it back up and see if you're right. Okay, did you get this? So number one, we have that inscribed angle that's a right angle, so it's 90 degrees, which means that its intercepted arc has to be twice that, or 180. And then we're also going to use the fact that these two chords are congruent, so their corresponding arcs have to be congruent. So if this arc is y, then this arc is y. Y plus 180 has to equal 360. You can go through and solve, and y ends up being 90. Okay? Number two, x and y are the measures of inscribed angles, and if you trace those angles out, they're intercepting the same arc, which is 110 degrees. Inscribed angles so x and y are going to be the same. And inscribed angles are half the arc, so we take 110 divided by 2, and we get 55. Okay? Last but not least, if we're going to inscribe a quadrilateral in a circle, then the opposite angles have to be supplementary. So 105 plus x has to equal 180. Subtract 105 from both sides, and x has to be 75. Okay? So how we use these theorems and kind of bring them all in together. And that's it. Okay? I know that's a lot. It's a lot to digest. Make sure that your spinner is filled in. And homework's out in Canvas. Have that done next time.